For today's class, we are going to cover Chapter 11, Sections 3 through 5, and have concept questions 11 and 12, and exercises 19, 25, 29, and 33. So I encourage you to go take a look at those problems, and then come back to this video, pausing as I pause to try and do as much on your own as you can. Starting with concept question 11. Okay, for this problem, we have a ball or an object that's moving with some speed, and it collides with another object whose speed is 0. And the first question is it possible for both objects to have 0 speed after this collision? The answer is no, because this is the before picture. The before picture has some amount of momentum in the system, so the P system initially is not 0. Okay, there is some momentum in the system. All right, now in the afterwards, if whatever happens, the final momentum must be non-zero as well, because assuming this collision, we're using our impulse approximation, or meaning that the delta t is super small, so no external forces can change this. And that's what we use for the definition of collision. It means that the initial and the final momentum must be the same. So if initially it was 0, afterwards it must be 0. Okay, now part B asks it a little differently. Okay, it says, is it possible for one particle to be at rest after the collision? If so, give an example, or if not, why not? So is it possible for one particle to be at rest after this collision? The answer is yes. And we have a couple examples of where that can happen. If these have the same mass, okay, if these have the same mass, then this one will stop, and that one will go and have the same velocity as this one, therefore the same momentum, since they have the same mass, meaning that the final system momentum will equal the initial. Okay, or if this one is huge compared to this one will bounce off and come backward and have the same velocity it had initially. So it can have the same, or the speeds, I should say, because it's opposite direction. So those are two cases, either the m1 equals m2 case, if this is 1 and this is 2. In that case, ball 2 will have the same velocity as the initial case, which satisfies our conservation of momentum. Or if we have m1 is much smaller than m2, so that m1 just bounces off of it, and m2 really doesn't go anywhere. Very good. Now let's take a look at number 12. Okay, we have these two ice skaters, and one of them weighs more than the other, and they push off of each other in the middle of an ice skating rink. And the question is which person has greater momentum after they push off of each other? So here's our two ice skaters. And before they push off of each other, the system momentum is 0, which means that is true after. So initial equals 0, and therefore that must be equal to P system final. Or in other words, if the final momentum is also 0, then the momentum of one must be equal and opposite to the momentum of the other. Okay? Or in magnitude, we can say that the two momenta of the parts of the system, the two people, are equal in magnitude, and they're traveling opposite directions. Okay, so if that's true, we can say that P1 final equals P2 final with a minus sign. We're just looking about magnitude in this question. And so their momenta are the same in magnitude, but opposite directions. And then the question says, well, what about the velocities? Are the velocities the same, or is one velocity bigger than the other? So the relationship between velocity and momentum is through mass. So this is the same thing as saying m1 v1 final equals m2 v2 final. And so if these are the same, then the one with the lighter mass will have the bigger velocity. So we can see that the velocities would be inversely proportional to masses, given that the momentums are equal. Okay, let's move on to some problems. Number 19, these exercises. Okay, 19, we have this bigger car, a 2,000 kilogram car, has a broken brake, and so it is slowly rolling, only at 100 miles per hour. Sorry, that's not slow. At 1 mile per hour towards a group of kids. And you see it, and you're going to try and save the kids. And so you hop into your smaller car, which only weighs 1,000 kilograms. How fast do you need to drive in miles per hour to hit the bigger car head on and cause it to stop? How fast do you need to go? This is a collision, and in collisions that means that momentum is conserved. And so we just have P initial equals P final. And so right before the collision, the two cars are moving, so we're going to have PA plus PB equals, and in the end, you want to stop the cars, so that means 0. There is none in the end. And we need to note that this means that one's opposite the other. Okay, so since these have vectors, I would say choose one to be negative, the other positive. All right. And so that means that in the beginning, PA is going to equal PB in magnitude. And so this is MAVA equals MBVB. And the mass of the big car is twice as big as the mass of the little car. We have 2,000, or sorry, let's go ahead and solve for the velocity of the little car. So VB is just MA over MB times VA. Plugging in our numbers, we get 2,000 kilograms over 1,000 kilograms times 1 mile per hour. So solving for that is going to give us 2 miles per hour. So the car that's half as much must drive twice as fast to have the same momentum as the other car because their momenta need to be the same in order to, in this collision, to have the final velocity, final momentum of the system to be 0. Okay, let's move to 25. Okay, so 25, we have this system here. We have one package here below, okay, and we're told it's of mass 2m. I'm going to call package B. We have another package here, we call that A, and we know it's got a mass of m. And it's on this frictionless chute, and the packages start at a height, I'm going to call that H0, or H initial. In fact, I'm going to use initial and final for my subscripts. H initial, okay? And the idea is what is going to be the, for part A, if this package slides down and hits this package and sticks together, then how fast will the two packages move together afterwards? So looking at this problem, how many different concepts can we see? Well, there's clearly going to be a momentum problem and an inelastic momentum problem because they stick together. But before that, this package is up here at rest and it's going to slide and speed up. And so that, in order to find the velocity of this package right before it hits this package, we need to use conservation of energy. So this is a two-part problem. One is conservation of energy to figure out how fast this box is going to be right before it hits. And then once we have that velocity, we can ignore this ramp and just say, okay, now we have a velocity right before, this one's stationary. We can do a conservation of momentum problem for an inelastic collision to find that final speed. And then part B is the same thing. We still find that initial velocity, but then we choose it to be a perfectly elastic collision, and this package A will bounce back. Okay, since it's lighter, it'll bounce back. And we want to find out how high will it go. So with those two ideas, see if you can go solve this problem. Remember that we have to first break it into a conservation of energy problem, and then we do a momentum problem. Okay, so to start with, I'm going to draw another picture here, A. So this would be the beginning of my conservation problem, and this would be the end of my conservation of energy problem. This will be the end. So to do that, I'm going to call this the state 0 and then state 1, and look at that in those ways. And so looking at that, choosing the system to be the ramp, gravity, and the box, so there's no external forces, no external work done. Then I'm going to say that K final plus UG final is equal to K initial plus UG initial. There's no friction, so there's no thermal energy, and there's no springs involved. So these are the only forms of energy I have. So in the final case, it reaches the bottom. Okay, so that's 0. And in the initial case, it's not moving, so that's 0. Which says that 1/2 ma V1, that's state 1, squared is going to be equal to ma and then GH0. I guess I'm going to use 0 for this. Alright, so with that, I can now solve for V1. V1, the masses cancel, and I'm just getting the square root of 2GH0. Alright, and I'm going to leave it like that. Okay, so now that I have the velocity of this box right before it collides. So I can kind of forget about the ramp now and just focus on this collision. So how would you set up this next problem then? Now that you know the velocity of this box right here, this one's 0, how are you going to set this one up? Okay, so your picture ought to have a before and after. You have a before, and this is going to be A is moving with this V1, I'm going to call VA1, and B is sitting there with VB1 equals 0. And then after they're stuck together, I'll just put them together, A plus B, moving at this final velocity. I'll be final. Okay. Let me call these initials to keep with the similar subscripts. Okay, so that's what the picture looks like. Now, how do we find B final? So I use conservation of momentum. So we're going to have PA initial plus PB initial equals PA plus B. PB initial is 0. And PA initial is just MA times VA initial, which VA initial is this speed. This is the speed of the box right before they collide. And that's going to be equal to MA plus MB V final. Okay, so V final then is equal to, you'll see that, MA over MB plus MA times VA initial. Okay. So plugging these things in, we know that MA is equal to, or MB is 2M and MA is M. So we get M over 2M plus M, or M over 3M, or 1/3 VA. So that's 1/3 VA initial, which plugging it into here gives us 1/3 square root of 2GH0. Okay. And I could plug in the 3 here, 9.8, and get a number, but I'm going to just go ahead and stop there. Okay, so the most important thing is we recognize how to break this into 2 parts. 1, a conservation of energy part, and 2, a conservation of momentum part, recognizing which variable that came from here was used here. Now this has a part B that's really good. It says, well, what if the collision is perfectly inelastic? So that means A bounces off and comes back up. Okay, so how would we approach that one? We already have the velocity of A right before the collision. How do we find the height that goes after the collision? How many concepts do we need to use now? Well, we need to do a conservation of momentum, only now we have our rules of conservation, or purely elastic collision, So we have our equations for that. But then, once we have that, we'll get a final velocity of A, which then we need to use conservation of energy again to see how high up it goes. So it's kind of the reverse of this process. We found this velocity with conservation of energy. We will do conservation of momentum to find the rebound velocity, and then do the reverse of this to find the height that goes. So go ahead and try that. Okay, so to try that, okay, we need to do our conservation of momentum. We've already found the velocity right before, so now we need conservation of momentum. So here we're going to use those equations for perfectly elastic collisions, and I'm looking for VA final is going to be equal to MA minus MB over MA plus MB times VA initial. And that's VA initial. Okay, that's what we had before. All right, now plugging in, we have M minus 2M gives us negative M. M plus 2M is 3M. Canceling that, that gives us a negative 1/3 VA initial. So with this certain relationship with M and 2M, we get the same speed, only this is for just the smaller box, and it's its rebound speed. That's what the negative is. But in magnitude, it's 1/3 of its initial speed. So now that we have that, we can find out how high up it's going to go. So we have this speed, and then we're going to say if we have this, we have our kinetic energy is equal to our potential energy. So now we're going to start with our K final plus our UG final is equal to our K initial plus UG initial. But in this case, the initial is down here on its way up, and this is the final. Wherever it reaches, it's going to reach some spot. So our K final is 0, and our UG initial is 0. Our K initial is going to be equal to 1/2 MA times this, and but only in magnitude. I don't care about the minus sign. So VA initial over 3 squared. That's our kinetic energy to start on its way up. And this is going to reach an MGH. I'm going to call it an H final. I'll go ahead and call it final. No, I'll call it H1 since I called H0 that initially. Okay, now the nice thing about it is the masses cancel there. So this H1 is equal to a 1/2G times VA initial over 3 squared. Okay, but VA initial is this one. That's how much it was before. 1/2G. Okay, squaring that one gives us a 2GH0. Squaring the 3 gives us a 9. Okay. See, the 2G's cancel out, and we get an H0 divided by 9. So it goes up 1/9 its height. Okay. Because the height is linearly proportional to the kinetic energy, but the kinetic energy is proportional to the square of the velocity. So this is a really good problem because we utilize two different conservation laws, conservation of energy and conservation of momentum. We practice with two types of conservation of momentum, or two applications of it, a perfectly inelastic collision and a perfectly elastic collision there. Okay. All right, so now let's move on to number 29. Okay, so for 29, we have these two ice skaters, and one is heavier than the other, and they push off of each other. They push off each other. So here they are. Oops. Here they are, and this is before. And then they push off of each other. So this is after, but now they're moving. This will be VB, this is VA, and this is the final state. they're moving. But what's the initial state? Well, VB initial equals 0, and VA initial equals 0. Now it is a collision. We call it an explosion, which is an explosion is the opposite of a perfectly inelastic collision where they stick together. Okay, this is just a reverse. They're stuck together and then they push off. Okay, and so with that, we know that the momentum must be conserved, but since initially it was 0, in the end the system momentum must be 0, so these must be equal and opposite. So with that logic, I can say that PA final equals PB final, or MA VA final equals MB VB final. So again, this came from the fact that our initial system momentum was 0, therefore at the end it should be 0 too, and these must be equal and opposite. All right. So we need to pause there for just a second, because what we're told is that the heavier skater reaches the edge of this ice rink, okay, in a certain amount of time. So now we have a different picture. We have skater A gets from there to there, which is some distance, it's distance r, okay, in some delta t, called delta TA. Well, skater B went to the edge of the rink too, in some different time, and we're trying to find that time. All right, so this is a two-part problem too. This is kinematics, and before we had conservation of momentum. All right, now we're given this time, and we know how big the distance is. So how is that connected to any of this? What variable here could we find from knowing these two things? We know that velocity, this is the velocity, assuming they're on ice, so it's frictionless. That's the velocity that travel with. So we can say that VA final equal to distance over time, r over delta TA. Okay. Now, delta TB is going to have the same relationship with VB final, only we're looking for it. So we're going to say that is equal to the distance over velocity, so r over VB final. Okay. So that means this one we need to solve for VB final. It's going to be MA over MB times VA final. Okay. All right, now with that, we can plug that in here and then solve for this time. I'm going to go ahead and do that. We have R over MA over MB VA final, which gives us an MB over MA, because it's reverse that fraction in the denominator, and then we have R over R divided by delta TA, which finally gives us MB over MA times delta TA. Those are canceled, delta T comes to the top. And before I plug this in, I just want to think about it. Okay, if we assume this is the one we know, this is the heavier person, so this is mass A, and A is bigger. Now A took 20 seconds. Do we expect the person who's lighter to travel faster or slower? We expect them to travel faster because if their momentum's conserved, the lighter person will have the bigger velocity, which means they cover this distance in a smaller amount of time. So our final result says that this time is equal to the lighter person over the heavier person. So this is a fraction less than 1 times this time. So it is a smaller time. And if you calculate it, that ends up being a 13, 3 repeating seconds. Okay. All right, so this is again another great question because we're utilizing conservation of momentum and then some basic kinematic ideas, okay, where we use just the very basic definition of velocity to do this. Okay, last problem. Let's take a look at 33. Okay, here is a two-dimensional problem. Now, this really is nothing new from what we've done before, except you have to be careful that momentum is a vector. So we have to consider components. So we have a ball of clay, call it MA, is traveling due west, VA initial, and I put a vector over it. Even though it's one-dimensional, I can put a vector because the other ball of clay is MB, and it's traveling due north. That'd be B initial. Those are two different directions, and therefore the momenta are in two different directions, and therefore we need to be careful to consider only components. So this is the before picture. What would the after picture look like if these two balls of clay collided and stuck together? Okay, so after, before, after that ball of clay will collide right there, and they must shoot off at some angle, which we're going to find. So this is going to be V final. I don't need to put a VA or VB because they're traveling together. This is going to be MA plus MB. Okay. So how do we find out how big this is, its magnitude, and how do we find what direction it goes? We apply conservation momentum in two dimensions, one for each dimension. So if I consider the x direction, then I say P system initial x must equal P system final x. Okay, well initially, the only thing that's got x momentum is this one. So this is just going to be MA VA initial, which I take off the vector sign because I recognize that's all of it. This is the whole thing is all in the x. All right, then I set equals, and the final momentum is this object, which would be MA plus MB times the final velocity x, the x component. All right, we can solve for that. We have VFX is going to be equal to MA divided by MA plus MB times VA initial. If we plug in our numbers, this is 20 grams. This is 30 grams, so the denominator is 50 grams. So we have 20 over 50, or 2/5. This is 3 meters per second. Okay. We're going to have 2/5 times 3, it's 6/5 meters per second. So that's the x component of the final velocity. Now we can do the same thing for y. Okay, we still have P system y, P system x, or P system final y, P system initial y. There's P system initial y equals P system final y. Only in this case, the only thing with momentum in the y direction is b. So we have MB, VB initial. Again, it's no vector because it's all in the y. This will be MA plus MB, V final y, which we can solve V final y in the same manner. MB sorry about that. And if we plug in numbers, we'll get 6/5 again, only just coincidentally. Okay, because of the numbers worked out, this was 2 meters per second. This is 30 grams over 50 grams, so we get 3 over 5 times 2 is still 6/5. So it's just coincidentally because of the numbers. But now we have the two components of velocity, and now we can find the final velocity as a vector. As we've done many times before, V final in magnitude is equal to the V final x squared plus V final y squared, which that's going to be equal to the 6/5 square root of 2, okay, since they have the same amount. And theta, since they're the same, we know theta is 45 degrees. But just to show that, we do theta equals inverse tangent of opposite over adjacent. So opposite would be y, adjacent would be x. In this case, it doesn't really matter because they're the same, 6/5 or 6/5 That's going to give us a theta of 45 degrees. All right, we are done for today.